Have you ever noticed how some of the most powerful tech in our world seems to use the same exact curved shape? You know, from giant satellite dishes listening to space, to the headlights lighting up our roads at night, there's this hidden mathematical blueprint behind it all. Well, today, we're going to decode that blueprint. We're going to unveil the secret shape that, quite literally, powers our world. So let me ask you this. What could a satellite dish, a car headlight, and the simple arc of a ball flying through the air possibly have in common? I mean, really think about it. One is pulling in signals from deep space, one is beaming light forward, and the other is just gravity at work. They seem totally unrelated, right?
Well, it turns out they're all secretly connected. They're all built on the exact same elegant, mathematically perfect curve. It's a shape that's hiding in plain sight all around us.
And that shape is the parabola. So let's just dive right in. You've probably heard that word before, maybe in a math class somewhere. But what is a parabola really? What's the fundamental rule that makes this curve so perfect?
See, it's not just some random U-shape that you can sketch. The parabola is defined by a rule that's so pure, so perfect, that it shows up absolutely everywhere, from physics to engineering. And to really get it, we need to look at its creation code, its DNA, if you will.
And the beautiful thing here is that the parabola is born from a super simple relationship. You just need two basic ingredients to make one. So, let's meet them.
First up, ingredient number one. Just imagine a single fixed point floating in space. We're going to call this point the focus. Think of it as our anchor point. Okay, ingredient number two. Imagine a single fixed line floating nearby. This line is our directrix. So that's our setup. A point and a line. These are our two key players.
Now here's where the magic happens. Let's play a little game. We'll introduce a new point, a moving point we'll call P. And the only rule of this game is this. Point P must always stay the exact same distance from the focus as it is from the directrix. It has to stay perfectly in the middle, distance-wise.
And if you trace out every single possible place that point P can be while following that one simple rule, the path it creates is a perfect parabola, every single time. It's not an estimate, it's a mathematical certainty. That one simple rule, equal distance, is the parabola's DNA.
Now here's where it gets really cool. It turns out that this little rule about distance doesn't just make parabolas. It's actually part of a secret family code. You can tweak it just a little bit to define a whole family of other famous shapes. And that code is called eccentricity. Don't let the name scare you. It's just a fancy word for a simple ratio. It's the distance to the focus divided by the distance to the directrix. And by changing that ratio, we can create all sorts of new curves.
So for our hero, the parabola, what's that ratio going to be? Well, it has to be exactly 1. Because, like we just said, those two distances are always equal. And anything divided by itself is 1. That's the parabola's magic number.
So check out the whole family tree here. If the eccentricity is less than 1, meaning our point always stays a little closer to the focus, you get an ellipse, kind of like the orbit of a planet. If it's greater than 1, staying closer to the directrix, you get a hyperbola. And right there, in the perfect middle, with an eccentricity of exactly 1, you have our parabola. See? They're all related, like cousins, all born from the same basic code.
Okay, so that's the geometric picture. But how do we describe this with algebra? Let's move on and decode the parabola's unique equation, its mathematical fingerprint. Here it is. This is the standard issue equation for a parabola that opens up sideways. Now, I know it looks pretty simple, but trust me, everything we just learned about the focus and the directrix is packed right into this little formula.
The real star of the show in this equation is that little letter A. It's not just some random number, it's basically the control knob for the entire shape. The value of A tells you exactly where the focus is. It tells you exactly where the directrix is. And if you change A, you can make the parabola wider or narrower.
Isn't that wild? All of that elegant geometry we were talking about, the focus, the directrix, that perfect curve, it's all encoded and controlled by this one tiny variable. Talk about efficiency.
Okay, but so what? Why do we actually care about any of this? What makes this one shape so special that we go and build giant dishes and powerful headlights with it? Well, this brings us full circle, right back to the beginning. The parabola has a superpower. It all comes down to how this shape handles waves. We're talking light waves, radio waves, sound waves, you name it. The parabola has this unique and incredibly useful ability to reflect them in a very, very specific way.
And this right here is the magic rule.
Imagine a bunch of parallel rays, like a signal from a distant satellite, coming straight in. No matter where they hit the inside curve of the parabola, they will all bounce off and get perfectly funneled to one single point. The focus. Every single one.
And what's amazing is that the superpower works both ways. For a satellite dish, it's a collector. Faint signals from space come in, hit the dish, and get concentrated right onto the receiver at the focus. But for a car headlight, it's a broadcaster. You put a tiny light bulb at the focus, and that parabolic reflector grabs all that scattered light and shoots it out as one powerful, straight beam to light up the road ahead. Same principle, just running in reverse.
So, from the arc of a basketball shot to the cables of a suspension bridge, that simple little rule of the parabola gives it a huge role in our world. The next time you see a satellite dish or a flashlight beam or even a water fountain, you'll know the secret. You'll actually see the focus, you'll see the directrix, you'll see that perfect mathematical shape doing its job. So the only question left is, now that you know the rule, where are you going to spot one next?